Hello dear students, welcome to Isomerism. Course title Pharmaceutical Organic Chemistry 1. Lecture title Classification, Nomenclature and Isomerism, that is part 1. So there are certain parts that I will cover, and it is module number 1 and lecture number 1. It is from unit number 1. This course, it is as per Pharmacy Council of India New Delhi syllabus, and it will be benefiting first year students in second sem of B Pharma. Myself, course coordinator, Mr. Dhamak Vikrant Murlidhar, affiliated to Savitribai Phule Pune University. Academic expert, Dr. Ramesh L. Sawant sir, and project name DTH Swayamprabha, sponsored by MHRD New Delhi. Let us see the learning objective of the session. So the first learning objective of the session is to study the concept of an organic chemistry. To learn an organic chemistry, one should know what is an organic chemistry. To study the classification of an organic compounds, and to study the concept of isomers and structural isomerism. So that is a part of your syllabus, that is structural isomerism. Now let us see the contents. First content, that is concept of organic chemistry. After that, classification of organic compounds. Based on the structures, classification of an organic compound, it has been done. So we will see each of the class with examples. And after that, isomerism. So that we will see. In the pharmaceutical organic chemistry 1, you are having a just introduction to an isomerism. In organic chemistry 3, you will have the details of in stereochemistry. So this isomerism, it is also a part of an stereochemistry, one of class, that is an structural isomerism. So that we will learn from isomers. So this, it is a class, that is structural isomerism. So based on the different structures of a molecule, isomers can be divided into certain classes. Now let us see the first concept, that is organic chemistry. There are certain chemistries, there are different branches of chemistries, like inorganic chemistry is one, physical chemistry is one, analytical chemistry is one, and one of the branch, that is organic chemistry. So chemistry, always you will deal with atoms, molecules and structures. But organic is a chemistry which deals always with an carbon containing compounds. So carbon containing compounds means the name organic, it has come from an living things. Actually the name organic, it has been derived from an organ. The organ contains a tissue, and tissue contains the cells, and cells contain the nucleic material, that is nucleic acid, that is RNA and DNA. And this RNA and DNA, they are made of an carbons. So you might be knowing that Watson and Crick model, so they discovered, and which was been rewarded with a Nobel Prize. So they discovered that the RNA and DNA, that is a nucleic acid, central dogma of life, they contain carbons in the structures, and the name, it was been derived from an organ. So that is a living thing. So the name, it came organic, and basically it means that it is containing an carbon. So organic chemistry is a branch which deals with the studies of structure, properties and reactions of an organic compound which contains the carbon. But there are certain molecules like carbon dioxide, sodium bicarbonate, sodium carbonate. These kind of molecules, they contain carbon, but they are not an organic compounds, because they are naturally occurring compounds, and their structural there are a lot many structural difference. They contain an inorganic metals and non-metals, so that is why they are not been classified in this organic chemistry. When it becomes an hydrocarbons, means carbon and hydrogen, so that will be dealt with organic chemistry. The range of chemical studies in organic chemistry includes hydrocarbons. So already I have discussed this. What is hydrocarbon? So which contains carbon and hydrogen. See, like gases, like methane is gas, right? So methane gas, it is an hydrocarbon. Hydrocarbon, why? Because it only contains carbon and hydrogen, as well as compound based on the carbon, but also containing other elements, especially oxygen, nitrogen, sulfur, phosphorus, which are included in many biochemical reactions, and halogen. So these are only certain chemicals which which are been attached with an carbon, so they come in an organic chemistry. Not when the carbon it is attached to an sodium, so that will not come in organic chemistry. So that will be a part of an inorganic chemistry. Now we'll see classification of organic compounds. So there are large number of organic compounds, and therefore a proper systematic classification was required. And this classification, it is based on the nature of carbon skeleton of an organic compounds. So there are two main classes. One is open chain and second one is closed chain. And open chain compounds are also called acyclic, and while closed chain compounds, they are called cyclic, because they are cyclic in nature, and all the carbons, they are intact. And open chain compounds, it will be a long chain, or it will be a branch compound, or it will not contain any kind of a chain. So that is why they are said to be an acyclic. Now let us see one by one class. Organic compounds, they are divided into two classes, that is acyclic or open chain compounds, and second class, that is cyclic or closed chain compounds. Now what is the difference between these two? So I will write the structures of some molecules over here. So I will write the structure like very simple compound, that is ethane. So ethane, you can see that there is no cycle and it is open chain. Or there may be some branch chain compound like isopropyl. I will remove one hydrogen. It does not contain and hydrogen. So this structure, it is of an isobutane. Why isobutane? There are 4 carbons, and at second carbon it is having the CH3 attached to it. So it is a branched one. So it is also been classified as an acyclic compound. Next class, that is cyclic. So cyclic compounds or closed chain compounds, like very famous example, it is an benzene ring. So benzene ring, it comes under a class that is cyclic or closed chain compounds. So one more example I will take over here, like see this, it is an pyridine. So there are further classification also of these classes, how it has been classified, so that I will write further also. Now this cyclic compounds, they are been divided again into 2 classes. One is homocyclic and second one is an carbocyclic. Homo, it means that it contains only an carbon. There is only a single atom, that is an carbon, and so they are called an homocyclic. Or carbocyclic, it means that it is containing only an carbon in the ring. So for an example, so this, it is an example of an example of an aromatic ring, that is benzene. Or I will write here a structure of an cyclopropene. It is written as a triangle. So this containing 3 carbons at the end, and here it is also having a carbon. So it becomes a structure of an homocyclic. Now what is the difference between homocyclic and heterocyclic? Heterocycle contains and one more atom. So this, instead of an cyclopropane, I will write an oxyren. This oxyren ring, it contains an oxygen in the middle. Like same example like this pyridine. Pyridine, it comes under an heterocyclic class. Further, these homocyclic compounds, they are been divided into two classes, that is alicyclic or aromatic. So what is now the difference between this alicyclic and aromatic? See, this kind of structures, like I will write here a structure of an cyclobutane or a cyclopropane. So both these compounds, they are coming under an alicyclic type of an class. Why alicyclic? Because it is not an aromatic ring. Aromatic ring means what? There are certain rules to be structured to be an aromatic. Like this benzene, it is an aromatic. Benzene, it is an aromatic structure. Or if I write an cyclobutane, I will write here a double bond. It does not become an aromatic. So it is an alicyclic kind of an compound. Aromatic are again been divided into two main classes. One is benzonide and second one is non-benzonide. So what this benzonide it means? Benzonide, it means it contains an benzene ring, or the structure it is almost like an benzene ring. So that they are called an benzonide. So for an example, I will write here one more ring, benzene ring attached to it. It becomes a structure of a naphthalene. Right? So it becomes a structure of an naphthalene. And non-benzonide structures like structures of an azulene. This structure, it is of an azulene, and see it contains 7 carbons in the ring, right? And there are some more carbons attached to a ring, but the ring contains 7 carbons. In case of an benzene, there are only 6 carbon. But this structure, it is an aromatic because there are 10 pi electrons, so it is an aromatic structure, while it is also an planar structure and it is a cyclic. So it obeys an Huckel's rule, so that is why it becomes an aromatic structure. Now further, heterocyclic. So heterocyclic, it has been classified again into two classes, that is heteroalicyclic and heteroaromatic. See, it is very similar to this class. Here it is alicyclic, here again it is alicyclic, but here it is an heteroalicyclic. So oxyren kind of an compounds, this oxyren kind of an compound, they come under a class that is heteroalicyclic. It means that they does not contain an aromatic ring, or they does not behave as an aromatic ring. Like a class for an heteroaromatic, heteroaromatics are like compounds, they like pyridine. Pyridine is an heteroaromatic compound. So let us see that heteroaromatic compound. And this heteroaromatic, why? Because it contains a nitrogen in the middle, and the class that is heterocyclic, because the cycle it contains an hetero kind of an atom in the middle. So these are some examples. I will write the name for your convenience so that you will understand. So the name of certain structures I will write. Here it is naphthalene. Here it is azulene. And here it is pyridine. And this structure, it is of an oxyren. So this oxyren, it is, so this it will be a structure of an oxyren. Here it is benzene and cyclobutane, and this it will become cyclobutene. Instead of N, you just write in. And these are simple structures like isobutane. So these are some representative examples from each classes. Now we'll see the second part, that is isomerism. We have seen the classification of an organic compound based on the carbon skeleton. Next part, that is isomerism. Isomerism is a phenomenon of exhibiting two or more compounds with same molecular formula but different physical and chemical properties. Isomers are the compounds showing different physical and chemical properties but same molecular formula. Say I will take an example over here. I've written a molecular formula that is C4H10. This molecular formula, it is often a carbon containing, there are 4 carbons, means it is often butane. So butane, see this butane molecule, it is an straight chain compound, and I will write one more compound over here. So that is also an butane, but it is having a little bit difference. It is an isobutane. It is a branch kind of a compound, but we see the number of carbons, they are 4, and number of hydrogens, they are 10. And in this compound again the number of carbons, they are 4, and number of hydrogens, they are 10. Only the difference between this compound is that it is having a different structural presentation. Means such kind of compounds are said to be an isomers. The compound showing different physical chemical properties but same molecular formula, and particularly and structures. So particularly and structures that come under a class of an structural isomerism. So there can be different like say this if we see an stereochemical structures, they are same but their configurations are different. They look similar but their configurations are different. Likewise, these both the structures they differ in the structure, carbon skeleton, they show the carbon skeleton difference, and that is why they are said to be structural isomers. Now what this isomerism differs in? Physical and chemical properties. So physical and chemical properties, it means that it may be a boiling point, it may be an melting point, it may be an refractive index, right? So that are the difference between this isomers. And chemical properties, it means like reactivity, it will be different for both the kind of a compound. So there might be some factors like steric hindrances, or that there might be an positioning of an groups. So it depends that chemical reactive, it will be also different because the structure arrangement, it is little bit different. Isomerism of an organic compounds can be broadly classified into 2 classes. One is structural isomerism and second one is an stereoisomerism. And this structural isomerism, it is also called constitutional isomerism. And stereoisomerism, it contains conformation and configuration, so that you will learn in further organic chemistry. Now you are having only a structural isomerism part. So what this stereoisomerism it means, I will explain in a short. See, the arrangement of atom in the space is different. Arrangement of atom in the space, it is different. It means that you might have heard about like cis and trans. So these are kind of in geometrical isomerism. So I will write here a structure of an cis and trans so that you will understand. See this, it is a molecule. Say suppose now what is the difference between these two molecules? Here it is having a chlorine group, right? Here it is also having an hydrogen, and same on the carbon, it is having chlorine and hydrogen. Only the difference is that arrangement of atom in the space, it is different. Now here it is having a chlorine, but on this carbon it is having chlorine on the upper side, and hydrogen in this case it is on the upper side, and in this carbon it is on the lower side. So depending on whether it is cis or trans, so depending on the arrangement of an atoms, what priority it has been assigned, so it will show that whether it is cis or trans. So there are some more classes in stereoisomerism also, like optical isomers, which can rotate the plane of polarized light. So they are called optical isomers. So that will be in your further organic chemistry, like organic chemistry 3, you will have this stereochemistry in the details. So you will learn over there. Now we will see only on structural isomerism part. Now we'll see the concept of structural isomerism. Already I've discussed this structural isomerism also. Structural isomers are those isomers in which the atoms are completely arranged in a different order with the same molecular formula. Already we have seen one of an example of an butane, N-butane and isobutane. I will write one more example from this class. I will write here an example of an ethanol and one more example, that is of an ether, dimethyl ether. See, in both the cases you can see the number of carbons are similar. There are only 2 carbons and number of hydrogens they are 6. Here also number of hydrogens they are 6, and there is only an oxygen in the middle, and here it is having an oxygen. It contains an ethanol functional group or alcohol functional group. This ethanol contains an alcohol functional group, and here dimethyl ether, it contains an ether functional group. So these kinds of an compound, see here the molecular formula, it is C2H6O. Both are having same molecular formula, but only there is difference of arrangement of an atoms, right? So at arrangement of an atoms, it is different, and so that is why they are said to be an structural isomers. I will write the name of this compound. So this, it is an ethanol, and here it is dimethyl ether. So why dimethyl? Because it contains an methyl, and this O, oxygen, it is an ether functional group. Now we'll see the classification of an structural isomerism. So depending on the carbon skeleton and depending on the further classes of an isomerism, depending on the structures, they have been classified. So first, that is chain isomerism. After that, positional isomerism. After that, functional isomerism. Next, it is metamerism, and last one, that is tautomerism. So we will see one by one isomerism from a structural isomerism class. So first one, that is chain isomerism. A chain isomerism occurs when there is a difference in atomic arrangement of a carbon to the carbon chain of a molecule. For an example, there are 2 isomers of butane. So the 2 isomers of butane, why? Because the structural arrangement, it is different. So butane, it has a molecular formula, that is C4H10, and we will see both the structures. Actually here it is comma. I will write here comma C4H10, C4H10, and one of them carbon lie in the straight chain, and whereas the another is a branched kind of a compound. I will write here the molecular formula, firstly C4H10, and second molecule, it is also C4H10. Only the chain, carbon chain, it is different. Already we have taken this example earlier also. So this structure now it resembles with the molecular formula, that is C4 and H10, and I will write one more structure with the same molecular formula, but structural arrangement, it will be different. So this molecule, it contains, now I will write the name of this compound, it is N-butane, and further molecule, it is isobutane. So chain isomerism, it refers when there is only a chain difference of an carbon, only carbon I am talking about, it is only limited to an carbon. When there is another atom, so that thing will be different. So N-butane and isobutane, so these are the 2 structures which belong to a class, that is chain isomerism. One is straight chain and second one is branched. Now further molecule, that is position isomerism. A positional isomerism arises when there is difference in position occupied by the substituent atoms or a group of atoms. The position isomerism, the basic carbon skeleton remains unchanged, but the important groups are moved uh, around the skeleton. So for an example, I will write here an example of an. So this molecule, it is chloropropane or propyl chloride. I will write the name for your convenience also. Now in this class, see number of carbons, they are again similar. Number of hydrogens, they are 7, and again chlorine molecule in this case also it is C3H7 and Cl. Now the difference between these two molecules is that uh, it does not refer to an carbon chain, right? It does not refer to an carbon chain. It refers to only a difference in an position of a functional group. So here the functional group, it is halide, that is chlorine, and there is only a difference of an position of a functional group. There will be no change in the carbon skeleton. So you can see that carbon skeleton is remaining same, only the position of a functional group it changes. I will write the name of this compound. So this compound, it is 1-chloropropane, and this compound, it is 2-chloropropane. 1-chloropropane and 2-chloropropane. So these are the two compounds where you can see the difference, that only the difference it is of a position of a functional group or in substituent atoms. Now we will see further, that is functional isomerism. The functional isomerism occurs when there is a presence of an odd form of a functional group with same chemical formula or same molecular formula. So for an example, a molecular formula, that is C3H6O, could be either propanol, an aldehyde, or an propanone. So I will write both the structures over here. This structure, it is of an propanol, that is aldehyde, and propanone. I will write the structure of an propanone also. It is an ketone. If we see the molecular formula, it is C3 and H6 on oxygen. Here again it is C3H6 and oxygen. Here the molecular formula is same, only the difference, that is functional group, it is different. So there is odd form of a functional group. Here it is an aldehyde. So the name of this compound, it is propanol, and the name of this compound, it is propanone. On, it refers to an ketone, and al, it refers to an aldehyde. Only there is difference of a functional group. In the first case, there was a chain difference of an carbon, that was chain isomerism. Second, it was positional isomerism, where the substituent atom position it was changing, and the third, that is functional group isomerism, where functional group changes, but the molecular formula remains same. Now further class, that is metamerism, have the same molecular formula, represents two or more compounds. They differ in nature of alkyl group attached to the same functional group. Now here the functional group will be similar, but there only the difference of an attachment of an functional group to the carbon chain. I will write here, there is a certain example, that is dimethyl ether. So I will write here dimethyl ether, and methyl propyl ether. I will write here the structure of methyl propyl ether. And third, that is isopropyl methyl ether. So I will write the structure of that compound also. So these are the three compounds: dimethyl ether, methyl propyl ether, and isopropyl methyl ether. Now the difference is that their carbon number of carbons are similar, number of hydrogens are similar, number of oxygens are similar. Means molecular formula is same. Only the difference is that attachment of an alkyl chain, it is different to an functional group. Here you can see that here it is ethyl chain attached to an oxygen, but here it is methyl and propyl, and here it is isopropyl plus methyl. So only the chain attachment of an carbon chain or alkyl chain, it is different to an functional group. Now the third class, that is tautomerism. See, now in case of an tautomerism, the molecular formula is same again, and only the difference is that it is in the form of an keto and enol. See, why keto? Because it contains a ketonic functional group over here, right? And this ketonic functional group, it has been interconverted into an enol form. So what happens, this lone pair, the pi electron between carbon and oxygen, it will break, and the lone pair on an oxygen, so that will abstract this hydrogen atom, and it will form an enol form. It is an alcoholic functional group, and as well as it is now having a carbon carbon double bond. Here it forms an keto, and here it will be an enol form. So this keto and enol form type of an interconvertible structures which are in dynamic equilibrium. Why dynamic? Because they are interconvertible, so that can be converted into a keto or enol form. At room temperature, keto form, it is quite stable and it is 99.9%, while enol form, it is very less, and so this keto form, it is quite stable, and when the temperature is rise or there is certain changes in the temperature, so it molecule will try to be in a enol form, that keto will be converted to an enol form, but keto, it is one of a stable form, and such type of an isomerism is called tautomerism. Now we'll see the further summary of the session. Organic chemistry, it is a branch of chemistry that studies the structure, properties and reactions of organic compounds which contains the carbon. After that, classification of organic compound based on the carbon skeleton, which broadly classified into two classes, that is open chain and cyclic compounds. Isomerism is a phenomenon of exhibiting two or more compounds with same molecular formula but different physical and chemical properties. And next, it was structural isomerism, are those isomers in which the atoms are completely arranged in a different order with the same molecular formula. And we have seen the different classes of structural isomerism in the details with an example, that is chain isomerism, positional isomerism, functional isomerism, metamerism and tautomerism. So we have completed lecture title, that is classification, nomenclature and isomerism, that is part 1, and in the next session we will start with part 2, and it is from unit number 1, that is module number 1 and lecture number 1. So thank you for attending the session.